now let's take a look at large sample estimations, section 10. So this is coming right from previous section on sampling distributions, and that you are sampling from a distribution. So you don't know if what you have of that distribution is normal or not. Most of the time it is, in which case you do not need a large sample to get a good estimate. So what you're doing is you're sampling of the population, and you're getting different possibilities, and how you do that sample will make a difference on how accurate it is. Like is it close to the actual mean? So this is our outline. It's quite a large section. First, we'll do point estimation. We'll just get to the general concepts right now. So this is types of estimation. So we're going to look right now at point estimation, and that's like estimating the mean, or the mean of a population. And then later we'll get into interval confidence intervals, and that's looking at like how you can say within this certainty the mean will lie in that range, or most of the data is in that range, that kind of thing. So here's an example or concept first to look at, and this is like target shooting. It's usually the example everybody gives. So in this target shooting example, let's look at these different possibilities. You can have this situation where the middle, of course, is the actual, say, mean, or what you're looking for. In this case, these first two cases, you are clustering all below the target and then all above the target. What we would say is this isn't a good estimation of the actual mean, and we'll define that in a bit. The next one has a bunch of shots all over, but it is clustering more around the target. Okay, and this has a wide margin, or we would say a large standard deviation, right? That's the idea. And of course this one is the best. So the middle is the actual mean of the population, or whatever estimate we're looking for. And this would be a good estimate of the actual mean, because we're making the assumption that we cannot know, or will not know, the actual mean, but we want to get as close as we can to it. Okay, let's continue with this discussion. Let's look at this one. Okay, and you can read the details in the book. This is right out of the book. Page 301 if you're interested. This is page 301. And let's define, so write this one down. So, do that top part, of course, as well. Write this one down. Let me, I'm just going to move some of my notes around here for a second. Give me a second here. Let's just move this up. Keep it all on one page. And then we'll zoom in on it. Okay. So write this definition down. An estimator of a parameter is said to be unbiased if the mean of its distribution is equal to the true value of the parameter. Otherwise, the estimator is said to be biased. We talked a little bit about the concept of biased and unbiased. So an unbiased estimator means, let's look at the bullseye situation. So these two cases for the bullseye concept would be biased. So these are two biased estimators, because the mean would be probably somewhere in here. That's probably the mean right there, I'm guessing, who knows. And similarly here, this would be the mean if you were to take the equal distance and kind of cluster it. So those would be biased, those two cases. Now this case here would probably not be a biased estimator, but it's not very good. They're spread out really far. So you have these distances, right? So it is not a biased estimator. It's just not good. Okay, and then this one, of course, is not biased estimator, and it's a good estimator. So the way we'll describe it is the standard deviation of the estimator for this one is large, and the standard deviation of the estimator in this one is small. So that's what you're looking for, is a smaller standard deviation. So let's look at this concept here again. An estimator of a okay, so it's biased or unbiased. So if this is the true value of the parameter, and we don't have to have it be mu, although that's the easiest one to talk about. So if this is mu, then this one is unbiased estimator, because if you clustered it around, so these would be your standard deviations, like this, and everything's clustered around the actual true value of the mean. The one skewed to the right here, we would say is a biased estimator. It's always off. Okay, and you could imagine sampling going on where you're going to get a biased estimator. So you have the true, let's say you have the true opinion. We talked about opinion polls in the book. So suppose you have a true opinion of an estimator, a true opinion poll, right? So it's something about, whoever, candidate, that kind of stuff. How you feel about something. So you'll never know the actual true case because you can't ask everyone. So you do sampling to try to get an estimator, and then you see what are most people say, what most people are in what range, or in this case we're talking point estimation, and that might be skewed or biased depending on who you're asking, right? So if you're only asking people that you call on an iPhone, then your messaging, then that might be biased. There's only certain type of people that maybe have that the iPhone. I don't know. Right, so that's what could happen, or certain times of night, like you're missing a whole group of people that that aren't around at 6 p.m. at night. So those are the sort of things that can happen. Even just calling and not getting because I mentioned, I think in one of my other videos, I don't ever pick up if I don't know who it is. If they ask me to do a poll, I'll say no. I just don't do it. So you're never going to get my opinion on a poll. So how many people are like that? So it depends, and it might skew the results. So those are sort of things you look at. So the spread of the variance or standard deviation is really the concept. Here's the next idea here. So this is your true parameter. It could be whatever you're in question. Most of the time it's the mean, the population mean that's accurate. But you are going to get different responses basically what you want is mu to be x bar. So if the actual mu is that, and you are figuring out which one it is, you're getting all these polls, and then you do an average or do a distribution of those cases, then you want that average to be the same. And frankly, in practice, that's probably really hard to do. People say it's better than it really is. We've seen examples of that in the past polling of different situations, and in fact it was wrong. All right, so things like that happen. Okay. Okay, so the distance is the next definition. I'll write this one out. So the next definition, talk about estimation, is this. The distance between an estimate and the estimated parameter is called the error of estimation. So the distance between an estimate and the estimated parameter is called the error of estimation. And that makes sense. Error of estimation, margin of error, that kind of stuff. That's all that's really referring to. So another figure we have here, do another bell curve thing. You have your true value right in between. Okay, and then you have your margin of error. Okay, so that's your margin of error. And we'll define those more carefully later when we get into the actual math of it. Let's see, so your margin of error, I'm not sure that's a really good picture, but it's close enough. Okay, and then an example, so like right in here, that might be a particular estimator, like one random sample of a poll. That's what you get. The true ones in between, but in what you'll get is that in most cases, every 95% will be in between here. And so what you get, I'll give you a number here. So between these values in here is 1.96 times the standard error. Same thing here, 1.96 standard error. And then these are the margin of error. Let's talk about the 95% confidence interval and where the 1.96 comes from, in case we missed it. They just kind of throw it out there. We talked about it earlier, but the 95% confidence interval isn't like a standard, like it doesn't have to be 95%. That just sounds like a good number. It could be 98, 97, 96. It could be 50%, which would be kind of lame, but but that's what we're looking at. So for 95%, basically it's the area between the z-score values. So if you look at, let's just do it over here. So if you look at z equal to negative 1.96 to z equal to 1.96, then the 95% is the 0.95, remembering that the area, and we'll get into more of this later, but this total area is 1, and so that's the 95%. That's the only reason we're using the 1.96 here. So the area between these values, is 0.95. Since we haven't done this a lot, I'll go through that with you. So using the table, remember that it's accumulated from left to right and it adds up. So let's go to the table, which is here. And I'll bring it back actually for a second. Okay, so the area that you're looking at, it's called the tabulated area. It's this accumulation. So you're accumulating oops, it's kind of large, huh? Accumulating this area from here to here. Okay, so that's what you're adding up when you look up the z value. So when you look up negative 1.96, It's just that little piece. And then the other values over here, that'll give you the middle part, which is what we're looking for. So let's look up the large. So you do large minus small, right? So 1.9. So here's your, let me do my pointer here. So here's your 1.9, and then you got to go over to 6. You come down and you look at that value, 0.9750. So write that down, 0.9750. And then you subtract the z-score of negative 1.96, which is this value. So when you subtract this value and this value, you get 0.95. Okay, so go ahead and do that. Okay, so 0.975, 0.025. 0.975 minus 0.025, I think. Just let me look at that again. 0.025, 0.9750. 0.9750, yeah, okay. So if we subtract those, we should get our 0.95. Use this guy. Okay, and well, you can see the 5s are gone, and the 7 minus 2 is 5, so I don't need to do it on calculator. It's 0.95, which is, when you convert to percent, that's 95%. So that's where that 1.96 comes from, and then it'll change. Later on, we'll talk about different confidence intervals you may want to get. Okay, let's continue. Look at a point estimator for population mean. So write all this down. Or a proportion, the distribution of the sample is approximately normal for n equal to greater than 30, which is what we talked about. That's by the central limit theorem. Thus, it's normally distributed, and we may use the empirical rule. So that's what we're basically using for these samples. So we use the empirical rule for the sampling distribution. And something you probably should know or memorize, but we'll go through it again. I don't always have it memorized, depending on the year. All right, so let's continue. So we're going to assume X bar, the sample, is unbiased. Or did you say unbiased? So what that means, again, is that the sample is random. It's done properly. You have a random sample of n equal to whatever. Okay, so that's what we mean by unbiased. So it's a statistical definition. So then, any sample mean X bar has a 95% margin of error of 1.96. So this is for we can assume that because it's a sample, it's a normally distributed sample. So it has a 95%, we say, margin of error of 1.96. That's your standard error. Okay, and so your standard error is calculated as your standard deviation divided by the square root of n. So that's what we will calculate and look up, or calculate, I guess. All right, so for 95%, we use, well, let me say this as well. So for 95%, we use, let me erase that part, and n greater than or equal to 30. Remember, that's the magic number for being normal. our margin of error is plus or minus 1.96 times the standard error, which is S over square root of n. So you're going to be at x bar, and you're going to do plus 1.96 times that, the standard error, and minus 1.96 times that. And that gives you an interval. It gives you a margin of error, but we're going to make that into an interval. So the point estimator and interval estimation, really the same thing. All right, so the idea is, when we get to the basic concept, so that is most of the time, 95% of the time, sample means will lie in the interval what I just described, negative 1.96 times S over root n to 1.96 S over root n. And this is more along the lines of interval estimation. Okay, let's do population proportion. Similar idea, just using those formulas. Okay, so for population proportion, we assume p hat equal to x over n is an unbiased estimator. And your standard error, these are all the things you'll be wanting to calculate above and this below, is the square root of p hat q hat, which is always 1 minus p hat, right, or p, divided by n. And if we look at 95%, so the 95% margin of error is that same calculation. It's plus or minus 1.96 for 95% times the standard error. So the standard error is that, the p hat q hat over n, the square root of that, sorry. And we have assumptions here for sample size. We have to assume that n times p hat is greater than 5, and these are all basically greater than 5, and n times q hat is greater than 5. So both assumptions on that. Okay, let's look at an example. And this one is going back to, we'll just do sample mean, calculate the margin of error in estimating mu. So calculate the margin of error. In estimating mu. So remember, you have a population, you don't know or cannot know the actual mean of the population. So you sample it. You do a sampling of the population, and then we're basically getting to say, okay, well, what's the estimation of how accurate that is? So in the sample, you sample all these things and you do the mean. Well, you're looking at the standard deviation. How spread out is it? And then you can come up with an idea like, okay, well then it has to be this close to the actual mean. That's the concept. All right, so this is just some numbers given. N equal to 100. S squared equal to 8. I always like to use S because if you can't find the mu, then how could you find sigma? Like how can you find the actual standard deviation? So it makes sense that you're really always looking at the standard deviation or the standard error or the not standard error. You're always using the sample standard deviation when you don't know the population completely. Okay, and then so where are we at? Okay, so let's do some calculation. So S is equal to the square root of 8, and that's I had to do this 2 times root 2, and now you get approximation. So that's approximately 2.83. So we'll use 2.83 for S. So going back to the margin of error is 1.96, etc. We can say the standard error, calculate that. I like to do them pieces and then put it together. So the standard error is S over root n. So 2.83 divided by the square root of n, which was given, which is 100, equal to 2.83. Root 100 is 10. So we just move the decimal, 0.283. So you get plus or minus 1 point. This is for 95%, which we will change later to whatever. And then that's times 0.283. And you get plus or minus 0.55. And so that's your point estimation. You basically say that that X bar is within plus or minus 0.55 of mu. But it's the same idea if you use interval estimation. So basically you say plus 0.5, oops, no, sorry. Left is negative. Negative 0.55 I'll do that again. So you're like negative 0.55 to positive 0.55. So it's within that estimation. Then we'll make that into an interval next. That's the idea. Okay. Let's continue. So do proportion on your own. So proportion, p hat, try one of those. Look at some applications. There's plenty in the examples, and the solutions are posted as well. Next, we look at interval estimations.